Hello, welcome to this presentation on 3 tools that can change a company that is reliant on successful engineering to survive and prosper. My name is Robert Halligan. I'm the founder and managing director of Project Performance International and a person who has lived and breathed pursuit of high performance engineering since 1985. The year in which I realised how incompetent I was as an engineer. I went looking for better ways of engineering things and discovered a substantial body of knowledge that was not being taught at universities, but was extremely helpful in achieving excellent results. I'm referring to the principles and the processes of engineering as contrasted with the emphasis in university undergraduate education on technology, physics and maths. The two together constitute the discipline of engineering. I embrace this newly discovered principles and methods body of knowledge with a vengeance, immediately producing much better results, and I'd like to think that I've subsequently contributed to the body of knowledge. I share with you today 3 process tools, amongst many others that exist, that I've developed and used extensively over the years, and that can really make a difference. Before moving to the tools, I would like to put what follows in further context. Project Performance International, PPI, is a company of like-minded leaders who thrive on helping others succeed. We consult and we train worldwide in the discipline broadly called systems engineering, which with some license can be defined as an approach to engineering that embraces fields like systems thinking, design thinking, product development and engineering management, all of which are concerned with problem definition and problem solving. PPI, which I formed in 1992, has so far consulted or trained physically in 41 countries across 6 continents, to a training alumni alone of over 17,000 professionals. You may see from the map PPI's staff and professional delivery footprint. Now let's look at these process tools. 2 of the tools are requirements related. The third is a project and engineering management tool. Tool 1, the first tool, is a unique requirements authoring pattern or template. Most attempts at authoring patterns have been subject matter specific and as such have met with limited success. This template, which I will call the Parsing template, is based on different concepts and is entirely general in its application and is extraordinarily effective. Now, before going into the pattern, let me place it in context by drawing your attention to this summary of a comprehensive scientific quality study by Carnegie Mellon University on the correlation between process-related activities and project performance. You see the various activities looked at there. For smaller, simpler projects, the single most beneficial activity was shown to be requirements development and management, the focus of this tool that we're about to discuss and the next. For larger, more complex projects, the project planning was the most beneficial activity, that is with the highest correlation coefficient, very strong positive correlation. And this is the focus of the third of our tools. As you'll see, also the requirements development and management activity also exhibited a very strong positive correlation for the larger, more complex projects. Compelling evidence of benefit. The role of requirements quality, or the impact of lack thereof, is also evidenced by numerous other studies, of which one is summarised here. So we've seen just the tip of the iceberg as far as evidence. Which brings us on to look thoroughly at the Parsing template, a case where one size does in fact fit all and with no compromise. Let me walk you through the template, which is based on the concept that within a requirement there are information pieces that must be present and information pieces that may need to be present. And you see the pieces listed there. Every requirement must have within an actor, and the actor is grammatically the subject of the requirement, and I'll assume natural language expression of requirements. So in that case, I'll say sentence, although the template is in fact can be used for any language, natural or otherwise. So every requirement must have within an actor. So the message switch, for example, shall switch. The message switch would be the actor. Every requirement must have within it an action. Shall switch messages. Shall switch is the action. The message switch shall switch messages. Shall switch is the action. And most function requirements need an object of action. Messages is the object of action. Now all that requirement says over the whole life of the message switch, it has to switch at least 2 messages of arbitrary type under arbitrary conditions. And of course, there's more to it than that. So let's add the remaining elements progressively. Now this will be, need to be done fairly quickly, of course, but I think you'll get the idea. The message switch, conditions for action. When in message switching mode, upon receipt of a message. Action shall switch. Object of action, that message. Huge improvement. But vague, let's reduce the vagueness by adding a constraint of action to. So shall switch that message within 10 milliseconds of receipt. But we still have problems. Let us reduce the problems by adding a refinement of object. For messages in ACP128 format having a valid routing indicator. Let us then add constraints of action 3. From the message input port to a message output port corresponding to the routing indicator in the message. And we have 3 constraints of action, 3 phrases. And then let's add an exception to action unless the message is of flash priority. Now, the other field is not used in writing requirements. It is the proverbial garbage can. It is used in another application of this template, which we'll go into a little bit later. You see the message now written in its full form. The message switch, when in message switching mode, upon receipt of a message, shall switch that message in accordance with IEEE 802.11g within 10 milliseconds of receipt for messages in ACP128 format having a valid routing indicator from the message input port to a message output port corresponding to the routing indicator of the message unless the message is of flash priority. And that is a singular requirement, single action, single actor, single action and single object of action. Our next tool is an overall very efficient, very effective methodology for capturing and validating requirements, or to put it more broadly, to achieve an adequate problem definition. You see from the concept diagram, and it is an analysis-based approach to that transformation of information from stakeholders into the problem definition adequate to drive the completion of development in an upfront approach or in an evolutionary fashion, depending on circumstances, driving development strategy. The low cost of this activity, typically 0.1% up to 2% of total development cost, compares very, very favourably with the historical costs of requirements problems that this technique largely avoids, those historical costs being 10, 20, 50, 80% cost overruns and total project failures. The methodology is illustrated here, starting with identification of stakeholders, as you would expect, and some techniques for doing that. Reading, evaluating, assessing what we're dealing with, identifying and resolving issues that affect our planning, and potentially measuring requirements quality. I think it was Drucker who said, you can't control what you can't measure, and I believe that to be pretty much the case. Measurement of requirements quality is telling us in a objective, repeatable and auditable way whether we have a requirements problem and feeding into an estimation of how big a problem we have. I'll come back to that. It's feeding into our planning. We plan the analysis like we plan any work, any engineering work or other work. And then we have a set of individual activities which integrate to provide this comprehensive, very effective methodology. And then we tailor the methodology down the closer the originating requirements are to already being good enough. And in the extreme, we might select just one of these activities to get us from nearly good enough to good enough. Or if where we start is far removed from good enough, we may do all of these things. We see here the concept of measuring requirements quality. The recommended metric, which I developed years ago and have been using for decades successfully, has, I should say, a number range of 0 to 1. 0 is total garbage, 1 is perfection. We can't get perfection, nor is it an objective. And any set of requirements has a value on this objective, repeatable, auditable scale. We see here a measured figure illustrated of 0.5. In a given set of circumstances, the metric figure aligns to a degree of risk due to defects in requirements. The calibration that you see there is fairly typical for non-trivial development of things of non-trivial importance. And a level of requirements quality corresponding to a medium level of risk due to defects in the requirements is illustrated, which says we need a higher standard. History tells us what that standard should be to get the risk due to requirements defects within a low band. And it is the work of system requirements analysis, to take us from what we have to what we need. We estimate how much work, and that, of course, is a part of our planning of the analysis. The drivers to that estimation are listed there. The estimation itself is, as is the quality measurement, a relatively short activity, typically an hour and a half to 2.5 hours to make one of these quality measurements. The first analysis that we will almost always plan to do is a context analysis on a life cycle basis, placing the system in the context of things with which it will interact, man-made things, naturally occurring things, purposeful interactions that are not purposeful but may still be relevant to requirements, and on a life cycle basis, whole of life basis, setting a whole of life foundation for everything that follows. We're in a similar time frame to the context analysis, which, by the way, captures and validates mainly external interface requirements and environmental requirements, with dribs and drabs of others captured and validated and specified. We move on to our design requirements analysis, which is done on existing specified requirements, looking for existing design requirements. Now, a design requirement is a requirement that directs that the system be built internally in a particular way. This analysis often results in the identification of invalid design requirements. About 90% of the design requirements being invalid is a common figure. Many of them being replaced by requirements of other types that accurately state what is needed. Often design requirements are there as a perception of solution, leaving unstated what is actually needed. And so the real requirements replace them. Some design requirements disappear without trace, and some turn out to be valid. We then move on to states and modes analysis, which is the first point at which we start looking at the behaviour required of our system and using the concepts and language of states and modes. This is a very high return on investment analysis, a fairly short analysis, but if there are major requirements issues, it is likely to identify them. It uses a form of state transition diagram, not the old Warden-Mallow-Haitley-Puribye ones, which are limited in expressiveness and inadequate in expressiveness, but a form using a suitably expressive notation, which you see here, and giving us the state mode requirements to have a state, requirements to have a mode, and requirements on relationships between those states and other states, modes and other modes, mode in one state, mode in another state, and defaults. Parsing analysis reappears, or at least the parsing template reappears, but now in an analysis role used on existing specified requirements to evaluate individually their adequacy. We parse an existing specified requirement into a blank template. We look at the pieces, look at the adequacy of each piece against quality criteria. If something's missing but should be there, we fix that. If something is okay, we simply validate it. If something is there but not okay, we fix it. And it's a very powerful technique. We see here from the... sorry, I went the wrong way. Let me go back. We see here the originating requirement, which is incomplete and unverifiable. And we see here a credible, sufficiently complete and certainly verifiable after version. Functional analysis, another enormously powerful tool, very widespread tool, but the widespread use of function analysis is generally in fairly basic forms, which are limited in their effectiveness. User stories and Jacobson use cases are what I'm talking about. They can be adequate in certain circumstances, but often are not. So we need also at our disposal a more robust approach, elements of which are illustrated here, and this approach to using functional modelling, suitable modelling notation that meets certain criteria. This approach allows us to determine what the system is required to do, using what inputs, from what sources, over what interfaces, delivering what outputs to what destinations, over what interfaces, and delivering what measures and values of performance. And for functional performance requirements on a life cycle basis, with a great deal of not just capture, but also validation, which neither user stories nor traditional Jacobson use cases provide. So it's a very powerful tool. Entity relationship attribute analysis generally reduces to data modelling and builds a data model where the entities are mainly or entirely inputs and outputs. The attributes are the attributes of the input or output, specification essentially, and the relationships are relationships that are relevant to requirements, relationships to be preserved, relationships to be verified as being correct, or relationships to be changed, or relationships that simply contribute to understanding the problem. We output from the model a list of entities and their attributes. We get a data dictionary. We extend that to non-data entries. We get an item dictionary. And that is a very useful tool in most requirement specifications for reducing the amount of work in development of the requirement spec and increasing the ease of use of the requirement specification. Now, when I use the term requirement specification, I mean a set of requirements in some form that can be a database, or it can be a document form. It can be digital, it can be screen-based, it can be hard copy, it can be whatever form we take, as long as we can view the information and the information relationships that we need. Value modelling. We have value modelling in the form of value of requirements, and we'll come back to that subject briefly later. We have value modelling in the form of building a value model of value added beyond just meeting requirements. A model that contains measures of effectiveness, which are characteristics, any characteristic of a system or service or a product or service that adds value beyond a threshold of acceptability, which of course is defined by requirements. And so associated with each measure of effectiveness is a threshold of acceptability, which corresponds to a requirement, and a target or goal or objective, which is under the label BEST on the value model that you see there. The priority and points columns are not necessarily used in communicating the model and using the model, but they may be used in building it, or they may serve other purposes. And then the weight column is linear relative value relationships between the improvements over the desired ranges, adding to 100%, giving contributions to an overall trade space. And then the value functions that you see there, the term UF stands for utility function, which is another term for value function used by the academics. The value function is showing how the value changes across the range from a threshold of acceptability to the target objective or goal figure. Now that information is brought together in a data file accessed by value modelling software. It's very valuable just for the insights that it gains and the rapport that it builds with stakeholders in building the model. It's even more valuable in carrying out trade-off studies in an objective and auditable way to gain insights into the merits of alternatives to support and to inform good decision making. Associated with system requirements are verification requirements, and their development is or should be an activity within system requirements analysis. Not a large activity, but a very, very valuable activity, costing about 7% of the total requirements analysis cost. So it's 7% of a small figure already, but adding huge value in avoiding under-verification and over-verification, and also avoiding disputes over the adequacy of verification. A verification requirement states the characteristics of evidence required that a system requirement has been met, and it drives verification design. No verification requirements, it's anybody's guess what verification design should be. A verification requirement can be as limited as just a directed verification method, such as test, demonstration, analysis, simulation, inspection, analogy, certification, to name the major ones, or more likely, slightly in the majority, it will be more than that. It could be a confidence level, it could direct a number of test cases, or something else. What you see here is also quite representative. So that's another activity within our system requirements analysis activity. Cleanup is a sort of small v verification activity. It may not be done with independence, although it may be. It's normally done on the output of the analysis set of requirements, searching against a set of words, parts of words and phrases that historically have been problematic in requirements. That words are and so on are not terms not to be used, but they are terms to use carefully and also to double check the usage of, and that's what this cleanup activity is doing. So we do a search on the list, eyeball the hits, make sure that where the term is used, the use is okay. It is not problematic. If it is problematic, we fix it. and that was requirements analysis, an overall methodology. The last of our tools is project breakdown structure development, or what is sometimes referred to as work breakdown structure development, even though work breakdown structure, WBS, is not or should not be a breakdown of work. If it is, we lose most of the value of it. We have an illustration here of a well-developed project breakdown structure, and I'm going to explain, walk through how to construct this, walk through what we get out of it. The top box is the overall project, defined by cost, schedule, deliverables defined by requirements and other information. So it's the usual project definition. Level 2 is constructed by asking the question, what products is a project to deliver? And the answer here, one of the answers here, has been 10 aircraft. Another answer has been a flight simulator. There are deliverable data also, and some integrated logistics support or integrated product support deliverables also. Next question. What services is a project to deliver? And the answer could be none, or in this case, there is an answer, aircrew training. Third question. What services are to be performed internal to the project that are not required uniquely to create just one of the products we have already or perform just one of the services we have already? There is always at least one answer, and it's always the same answer, and it is project management. There is here a second answer, which is insurance. And then the fourth question, what products, if any, are required that involve resources that are required to create more than one of these products or perform more than one of these services. That is, that transcend two or more of the elements we have captured so far. And the answer could be nothing, or in this case the answer is a new factory. This is a product-oriented project, so we'll start with a product, 10 aircraft. What products are to be brought to bear to be created to result in the creation of the 10 aircraft? Answer, a non-deliverable first article aircraft, so that goes on, and 10 production aircraft. What services, in addition to those two products, to result in the 10 aircraft as supplied, or as defined, I should say? And the answer is delivery. What products, in addition to the deliverable products that we haven't picked up already, need to be brought to bear? Same story, same criteria, and the answer is none. There's nothing extra. First article aircraft, what products? We don't know, we haven't designed it yet. Stop. This is an evolving structure. Now, if the situation was as I describe, eventually they have designed it. So eventually that question can be answered, which may be progressively, or it may be as a single activity, with airframe, propulsion system, flight control system, environmental control system, weapons system for a military aircraft, electronic warfare self-protection system, and fit-out as the answers. What services? Aircraft system requirements analysis, aircraft system design at this physical level, aircraft integration and assembly at this physical level, flight test, qualification test, and the incremental efforts to achieve aircraft certification are the answers. And then a third question, what products that are not deliverable products incorporated as a part of the aircraft, but still involve resources are to be brought to bear? Again, same qualification regarding transcending two or more elements. And one answer is a wind tunnel, and a second answer is a new avionics laboratory. So they go on. You see their project management. And some entries below it. It's a service. What services are to be performed to result in the performance of the project management service? Answer, project planning, project administration, and project control. what products are to be brought to bear that involve resources that are required to, or not just required to perform just one of these services, that is trans something or other, get the right word, transcend is the word, transcend two or more of the elements we have so far, and one answer is a project management information system, and the second answer is a new Mercedes for the project manager. Now guys, what we get from this structure is a framework for costing. Every dollar in the project is in the level 2 elements. Every dollar in the 10 aircraft is in the level 3 elements. Every dollar in the first article aircraft is in the level 4 elements. We get a framework for scheduling. Each of these elements has a start, a duration, and a finish for its creation or performance, as the case may be. And there are dependencies that can be modelled to give those. Framework for scheduling. We have a framework for definition through requirements on the products and requirements on the services. We have a framework for risk analysis. Everything that can go wrong in the project can go wrong by a product not being created correctly, a service not being performed correctly, for internal reasons, or through failure to get some necessary input from the outside world. We have a framework for risk analysis. We have a framework for measurement and for assignment of responsibility. And as soon as we have measurement and assignment of responsibility, we have a framework for reporting. And we also have a framework for organisational design. Here, teams shown, teams responsible for identified in the diagram elements, and team design with, we see down the bottom there, subordinate team leaders being members of the superior team, and we also see horizontal relationships of cross-team membership to give representation on one team of another team and vice versa. A framework for organisational design, most of which we lose if we would have simply a functional structure. Enormously powerful tool. There are other high return on investment techniques. I mean, they're also very common techniques that I won't go into. The use of compromise impact values as an objective way of valuing requirements is a very sound and useful tool. The use of decision and event trees for supporting decisions involving what I call event-based uncertainty. Something will or will not be available by a certain date, or we will or will not get some approval or licence, and providing insight into the merits of the alternatives. Performance threat analysis, a terrific tool for iterative performance optimisation, reduction of risk arising from the possibility of failing to meet performance, and avoiding excessive design margins. Requirements quality measurement we've talked about, providing an objective criteria for good enough requirements, which generally means low risk due to defects requirements. And used for many things. I illustrated using it for estimating and planning, but there are many other uses of that quality measurement. System effectiveness modelling, we've just illustrated that. Implementing the very simple principle of identifying feasible solution alternatives, that is, can meet requirements, and pick the best. And the effectiveness modelling gives us the reference for picking the best and for optimisation. And then we've mentioned verification requirements, providing an objective basis for verification design. PPI provides many resources to PPI clients, and many of them available to the engineering community in general, a way of giving back to the community. We see here a list of, for example, data item descriptions. I'll just pause for you to have a chance to have a glance down that list. It's a very comprehensive set, and I believe very high quality, I believe, higher quality than available in any of the public domain resources that I know of. And also an example document set. So we have data item descriptions or templates for key information types, and here we have examples of these key information sets involved with a coordinated set, starting with a capability system, a system providing a capability through capability engineering to identify technology items that are to form a part of the solution, products and services, and engineering artefacts associated with that whole development of a solution, all related to one another. PPI also publishes, and I think these are downloadable from our main website, application guides on the various systems engineering standards intended for general application, and also one domain-specific standard, which is the European Space Agency ECSS 10 Systems Engineering Standard. There's a watch this space for an application guide on the next version of ISO IEC IEEE 15288, which is not that far away. It's in committee draft 2 at the time of recording this presentation. There is more. We publish 3 practice guides, requirements capture and validation guide, requirements specification development guide, which has more detail and content that I believe you won't find elsewhere. It is very valuable, and a military capability development guide, all substantial in volume and content, and professionally produced. There is also for PPI alumni and clients and guests our systems entering Goldmine, which provides access to about 4 gigabytes of curated systems engineering documents and a searchable definitions database of over 7,900 terms used in systems engineering or related practices. And it also, just let me go to the next slide, has as a component of it and linked to it the Systems Engineering Tools database, which is a jointly developed and operated database of systems engineering software tools and cloud services jointly developed by PPI and INCOSE, with a home page that looks like this, and providing search capabilities for tools, for tool vendors, and also on a mapping to and definition of PPI systems engineering process elements, which collectively comprise the totality of systems engineering practice, and also a mapping to and definition of systems engineering processes, and also topics defined by the INCOSE Systems Engineering Handbook. So it's a very substantial resource, and I think you'll get some idea of what's there from just the introductory page, the home page, which you see here, but also some navigation pages with example synthetic tool data. And then the access to it is for INCOSE members and PPI account holders. PPI also publishes a monthly systems engineering Newsjournal, PPISYEN, also available to our alumni and clients, and also available generally on the PPI home page via links from the home page. And again, a substantial publication, 30 to 60 pages monthly, and full of systems engineering content, articles, knowledge pieces, news pieces, and other content. some contact details for our locations around the world. And that's it, folks. Thank you for your interest. If you have any questions, I'd be happy to take questions by email, or you could track me down via LinkedIn, and happy to chat with you by LinkedIn.